Joe, how y'all doing? Plan today will be to work through a few uh, electrodynamics problems. We'll see how that goes. We'll check and make sure the volume and everything is okay. Seems to be good. Anybody notices an issue, let me know. Hmm. Can't tell. Streaming at the moment. Let me check. Right, looks good. So the problem at hand will be problem from older physics that my electrodynamics professor went over. So basically what we have is a resistor on a metal bar and a rail can fit across it and slide along it. It has a mass. This distance is L, and we will look at it moving with a certain velocity V. Bar mass M, sliding on two parallel conducting rails. Resistor of resistance R. We have a uniform magnetic field into the page. So in this entire region, there's a bunch of there's a consistent magnetic field covering the entire region of the track. We want to know if the bar moves at a speed V, what is the current in the resistor? Two, what is the force on the bar? And three, if initial velocity is V naught at t equals 0, what is V at t? Right, so we'll see how to solve this. So the first thing, The bar moves at V. What is the current in the resistor? Just like we'll be using the equation. Flux is the magnetic field dot dA. Should be the divergence of the magnetic field in dA equals B dot A. Basically, I'm integrating the surface. So to add a few steps, this would be the magnitude of B, the magnitude of dA, cosine of theta. And looking at this, the area will be this box here. And the magnetic field is going perpendicular to that box, is going into the page. So the angle between them is 0 or 180. You know how you want to look at it, but we'll look at it as 0. It means this is 1. And if you add up the total, all of the area of this thing, we just call it A, the total area. We can work out what that is later. We can say it gave us L, but we call this our axis. This is X, this is Y. So that'll be X. So that's BLX or BLBX. So I'm not sure why we don't integrate that, but the official answer so far is the flux. I should say the magnetic flux. The magnetic field going through the page times the area that is going through, which is the length times uh the length times the distance, which is this red box right here. Uh, so what we'll do is we'll take a derivative of this with the understanding that the derivative of the flux actually, let me add a few more steps. So we have magnetic flux equals BLX. I'm going to take a derivative with respect to time of both sides of this. So that equals, so the magnetic flux is not changing, the magnetic field is not changing in time, the length is fixed. So we would have to move that to dx over dt, which equals BLV. That's all that is. And I'll just keep in the back of my mind, what if we ended up having to integrate something? I guess you can't necessarily integrate d dx dt. So I suppose that's why. And we also know that the electromotive force, which is similar to a voltage, is going to equal the negative derivative of magnetic flux. That's going to equal negative BLV. And we also know that the magnetic flux, the electromotive force or the voltage, is the current times resistance. So So that means that E equals negative BLV equals IR. So that means that the current going through this bar is negative BLV over R. The equations that we use, we use that magnetic flux equals the integral over an area of the magnetic field dot product the area. We use the fact that the derivative of magnetic flux is the negative of the electromotive force, is similar to voltage. We use that voltage is the current times resistance. And the official way of writing this one is negative. All right. It's easy enough. And I wonder if these three are going to be on our formula sheet. Like, just like it is, it's just in a more compact form. So basically, since the magnetic flux is the integral of B dot dA, and the electromotive force is the derivative of the magnetic flux, we could just put these together and say E equals negative D magnetic flux over dt, which equals d over dt, the integral over a surface, magnetic field dot dA. This is the one that they have on the formula sheet. Oh, got my negative. Right, so it's there with a little bit of, and they call this Faraday's law. So this combined with E equals IR. So technically it's two equations. Faraday's law in the definition of voltage. And the next one is, so it looks like we have this bar. We're manually moving the bar, which is changing the flux, and that's inducing a current. So since the bar is moving this way, which is increasing the flux in the red box, which is enlarging, the flux is increasing downward. So the induced magnetic field is going to want to come out the page to counter that. That means that the induced current must be going this way. we can use this equation. Let's see what it's called. See a ready name for this one, but they come to me. Magnetic force equals the integral of the current cross product, the magnetic field, integral over the loop line integral. And then it's not apparent on the formula sheet, but it may just be in a different form. We have the magnitude of the magnetic force equals the line integral magnitude of I, magnitude of B, sine theta dl, and the current and the magnetic field perpendicular to each other around the whole way. Magnetic field is in or out to the page. The loop is on the page. So this is going to be 1 sine of 90 is 1. And the loop should have the same area. This will be IB, uh, and the loop should be LX. I'm thinking of this properly. And I, we have from up here, is negative BLV over R. We want the magnitude, so we'll get the positive. I believe the length is just this length here in this equation. Am I understanding it properly? So the length we're dealing with is just this. Right? We don't need this X. This would be the L squared V over, and the force would be to the left to oppose the movement. So this will be F. Trying to oppose what's increasing the flux. So it's slowing it down, so it'll stop eventually. Think about that one. There's enough to keep going. And C says if initial V equals V naught at T naught, what is V at T? Well, it's going to be 0. Eventually, since F V counters V at T, V equals 0. So let's look to the next one. Now we have a loop. Say that the magnetic field is B naught I, and we'll call that out of the page. A loop with mass M. It is L long, W wide, and the resistance is R. And at this, so that's why this is a X direction, because this is the up direction. So this thing is falling, but X is out the page. This is Z in this direction. It's falling under the influence of gravity. So F equals mg. That's pulling it down. And T naught, which is where we're starting, V equals negative VK. What is the magnitude of the terminal velocity? So we need to get the current to find out what the force. So basically, it's a similar process as the last time. So we have the electromotive force equals, now look at the formula sheet, negative V over dt integral surface B dot dA V equals IR plus I equals epsilon over R, and F equals the integral cos B, dl, and it's going to be over 4 different loops because we have a square or rectangular loop. So these are all the equations we should need. E equals negative d over dt integral, should be able to just say b l w. I mean, I need to do a double integral. Let me make sure that looks like what we can do is first we need to get the direction. So this thing is falling this way. So the area here is shrinking. So the flux is decreasing out of the page. So the loop wants to make a flux to counter that. So the induced magnetic field is also going to be out of the page. That means my current in the loop that's induced is going to go like this. Induced. Should call the up. Wow. See how this goes. So what's going on is I have my integral generally right. It's just that the height, the z component is going to change with time. We just call that z of t, or I can call it L of t. Doesn't really matter. With this fixed, be negative b L dl over dt with equals negative b L v omega or w for the width. That's my electromotive force. We have V equals E equals IR plus I equals negative B L V W over. The L there. L is LOT, which becomes VDW, and that's VOT, right? That's our current. So now all I have to do is get the force. One, looking at this. So the velocity here is going down in the same direction of the current, going that way. So the force on the left side, let's call this side 1. So the force on 2, the force is this way. The force on 1 is this way. So they cancel out, which means the force left over will be here in the up direction. So we'll have to do one integral. This one down here is not giving any force since it's outside. Um, and the length, so the current and the magnetic field is definitely right angles to each other. Just say B, and the length of that segment is the width, which is W. So we can say B squared, W squared, VT over R equals the force equals mg. Newton's always counts. So the velocity is going to be mg divided by v squared w squared vt times the resistance, double my vt. That'll be the velocity, and terminal velocity is when acceleration is 0. So Do this integral again. This time, keep it in terms of see, this is the terminal velocity. Some details I'm not seeing in this one. So this one is 1. Then still have to add, if I call this 3, but it does still have the FG force. So that's plus FG, or I should say plus MA. Plus, I should say minus MG. This is 1, 4, and we'll say that all of this, the net force, F net equals MA. Terminal velocity when A acceleration equals 0. So then we have B squared, W squared, VT divided by R equals mg. And then we can solve for VT or VF, V terminal equals mgr over B squared, W squared. Right. That's enough on this for now. I'll see y'all next time.